Greetings. Today you are viewing the capstone video for a mechanical engineering project that took place during the fall semester of 2015. My name is Kevin Cass. I am a mechanical engineering and nuclear engineering major. This semester I worked with Derek King, a mechanical engineering major, Harrison Rule, an electrical engineering major, and Sean Soroka, another mechanical engineering major. Our project sponsor was Amphenol Advanced Sensors, a company which designs and produces temperature sensors that are used in a wide variety of markets, including aerospace, automotive, healthcare, and industrial. Amphenol tasked our team with producing a test bench, which was capable of producing uniform airflow at 70 meters per second and 300 degrees Celsius. We were successful in completing our design, which includes a blower and heater connected in line in the side of the test bench. This is connected to the rest of the assembly via 6-inch steel pipe and a 90-degree bend. The next part of the design is the flow conditioning section, which includes 3 meshes and a nozzle, which reduces the diameter of the pipe to 3 inches. This allows us to reach desired flow characteristics within the actual test chamber itself. Above the test section is the test apparatus, which includes a standard factory actuator slide connected to a fixture that the team designed, which allows for the safe testing of a variety of temperature sensors. The entire system is controlled using a rugged thermocouple, which records temperature, and a keel probe, which records pressure. Unfortunately, the team was unable to build a full working prototype due to costs, but we were able to produce a scaled prototype, which would allow us to verify that the flow within the test chamber was uniform. The major factor affecting the cost of the prototype was the elimination of the heater, which allowed for cheaper materials to be bought for the remainder of the assembly. Now, let's examine what the construction and testing of that prototype looked like. Once we'd ordered and received all of our materials, the next step was to cut PVC pipe. A lot of PVC pipe. After the pipes were all cut, we took a trip to Lowe's to pick up some last-minute materials and a little something to add some aesthetic appeal to our design. Once we'd finished all of our spray painting, the real work could begin. We assembled the individual 3D printed components of the testing fixture and then connected that fixture to the test section pipe. We also drilled a hole where the temperature sensors could be inserted into the flow and covered that hole with silicone film. We then test fit the entire assembly, including meshes, pipe, and fittings, before fixing everything together with PVC cement. It turned out getting the pipes in the fittings was much easier than getting them back apart. Once everything was put together, we drilled a few holes which would allow us to insert a pitot probe which we would use to characterize the flow, and our rig was finished. It was quite a sight to behold. For the testing itself, we borrowed a 1.5 horsepower blower from the laboratory of Dr. Savas. Once everything had been hooked up, we used a pitot probe to record the pressure in various components of the assembly. This allowed us to create velocity profiles, which demonstrated that the flow was uniform in the test section. At this time, we would like to thank our project mentors, Mr. Stuart Wells and Jason Detch from Amphenol Advanced Sensors, for sharing with us their expert guidance throughout the course of the project. We would also like to thank our professor, Dr. Savas, for his support, his guidance, and the use of his equipment for testing. Upon reflection, this project proved to be an excellent way of testing all of the theoretical knowledge gained in the classroom. It now stands as a major highlight as each of us prepare to graduate from Penn State and begin our engineering careers.